Okay, I just had to do something on this, since I'm sure a lot of you noticed the recent headlines about the Kepler probe, or the Kepler telescope, and how it's supposedly now just recently gone into emergency mode. I just got a real kick out of reading these articles and learning about the whole alleged history of Kepler and its failing gyro wheels over the last couple of years that supposedly keep it stabilized, and how the Kepler 2 mission, the K2 mission, claims to use solar pressure to keep the satellite stabilized. So I just found all this completely hilarious, and just wanted to throw some stuff together that I found and share it with everybody and let you all see what you think. So here you go.
NASA is scrambling to save a $600 million spacecraft that's gone into emergency mode. Experiencing what one researcher called a spacecraft emergency, the Kepler Space Telescope is now rapidly burning through fuel, and NASA is running out of time to save it. Engineers first discovered the telescope was in emergency mode Thursday, and believe it actually entered that stage at least a day before. One of the biggest obstacles engineers now face is Kepler is 75 million miles from Earth. Even at the speed of light, signals take 13 minutes to go between Kepler and NASA's home base. It's unclear what's exactly wrong with the spacecraft, but it might not be an easy fix. NASA scientists will have to find a way to repair Kepler with whatever the spacecraft already has on it. Engineers fixed a different major problem in 2013 by using pressure from sunlight to keep Kepler steady. NASA's poured a huge amount of money into the Kepler project. The spacecraft launched in 2009 and was only supposed to take 4 years, but severe breakdowns and hard-to-read data have plagued the mission. The Space Telescope's mission is to search for planets that could potentially hold life. By the beginning of 2016, Kepler had found 1,000 of those planets. For Newsy, I'm Ryan B.
In 2010, the Japanese Icarus spacecraft became the first probe to successfully propel itself through space using nothing more than light from the sun. That's because it had a solar sail, which is just like a regular sail, except that it uses light to push itself along instead of wind. Icarus is still out there orbiting the sun, but back here on Earth, scientists are preparing for new missions with solar sails. Even though we didn't really start using them until a few years ago, most of the physics behind solar sails were worked out in the early decades of the 20th century. That's when physicists who studied relativity and quantum mechanics like Albert Einstein, Max Planck, and Louis de Broglie showed that photons that make up light have some weird properties. It might help to think of photons like little massless, sizeless tennis balls that are also waves at the same time, because photons act as both particles and waves. Okay, so photons aren't really like tennis balls, but they kind of work in similar ways when it comes to momentum. When a tennis ball hits something like a chain link fence, it transfers momentum to the fence, which pushes the fence in the direction the ball was moving. Then the posts pull the fence back, which is why it rattles and swings back and forth. Light pushes solar sails in pretty much the same way, but there are no posts to keep them in place. Light hits the sail, some of the momentum is transferred, and the sail is pushed in the direction the light was moving. There is one big difference though. Photons don't have mass, and tennis balls do. And an object's momentum is usually defined as its mass multiplied by its velocity. Since 0 times anything is still 0, massless photons seem like they shouldn't have any momentum to transfer. Those physicists in the early 20th century, though, showed that photons managed to have momentum without any mass. Instead, a photon's momentum is proportional to its frequency, how quickly it oscillates back and forth as a wave, instead of to its mass. That means that different colors of light have different amounts of momentum. Blue light has a higher frequency than red light, so photons of blue light have more momentum than photons of red light and would push a solar sail more. When light pushes, it's called radiation pressure, and it's something that space scientists have been using and accounting for since the early 1960s. Like when they were designing the Mariner 4 Mars probe, for example, which used radiation pressure to stabilize itself and make sure it stayed on course. Because they compensated for the push from sunlight, Mariner 4 became the first probe to ever return pictures of another planet from deep space when it sent back images of Mars in 1967. Radiation pressure is also being used to keep the Kepler space telescope stable. We've talked about Kepler before. Its main mission was to find planets around other stars by staring at them for years at a time. To do this while orbiting our sun, Kepler needed to be able to rotate slightly every once in a while so that it could keep an eye on the same patch of sky while it moved. But in the vacuum of space, friction won't stop you from rotating once you've started. So Kepler had what are called reaction wheels, which would basically spin in the opposite direction to stop the telescope from rotating out of control. In 2013, when 2 of these reaction wheels stopped working though, it looked like Kepler's days were numbered. But in 2014, the team working on the project was able to use the sun's radiation pressure to change where the telescope was facing. And it's still working more than a year after the fix, all thanks to light's ability to push. It's one thing to keep a ship stable, but for radiation pressure to be a practical way of propelling a spacecraft, solar sails have to be huge, like tens or hundreds of square meters, because there needs to be room for a lot of photons to hit it. To give you an idea of how small a photon's momentum really is, it takes about 2 million billion trillion blue photons to match the momentum of a single well-served tennis ball. But following the example of Icarus, some of the missions planned for the next few years are going to use solar sails. The Planetary Society, a group whose founders include Carl Sagan and whose current CEO is Bill Nye, is planning a mission for 2016 that they call Light Sail 1, which will orbit around Earth with the solar sail big and reflective enough to be seen from the ground. And NASA's Near-Earth Asteroid Scout mission, slated for July 2018, is going to test out a solar sail on its way to scope out near-Earth asteroids. Both of these missions are going to be unmanned, but there's no reason why solar sails can't be used on missions with humans on them someday, moving through space using only the pushing power of light itself. Thanks for watching this episode.
Also, check this out. This is some guy, I think it's at a SETI conference, talking about how the Kepler telescope actually works, supposedly. And it's pretty hilarious. So, all these claims that all these people have gotten so excited about with all these exoplanets that they've been discovering are nothing more than a few pixels that they extrapolate out into all this data, supposedly. And this is pretty hilarious too. So here, check this out.
So Kepler launched in 2009. Its mission lasted nearly 4 years and ended in 2013. The point of the mission is to simply turning pixels into planets. Kepler doesn't make beautiful images typically like the Hubble Space Telescope. Hubble can use their images to show off their findings, and you can see the beautiful things they find. With Kepler, our images aren't beautiful. They look like fuzzy blobs. The top left here, they're beautiful to some people, but to the public, perhaps not. I think it's stunningly beautiful and amazing things we do. But so the top left here is what one of our stars look like. It's just a few pixels with a star falling upon it. This star happens to be Kepler 10b. This is a 2-dimensional representation of data. You then take that 2-dimensional representation with a time axis and turn it to a 1D representation. So that's basically measuring the brightness of this star, these few pixels, continuously over time, and looking for little dips. This one slide hides in it many dozens of years of work from an incredibly dedicated and talented team of people at NASA, Ames Research Center, who built this pipeline to simply do this. So I'm brushing over this amazing work, but understand this stage is incredibly challenging and difficult, and all our discoveries rely upon this work. So here you see one transit. This is the Kepler 10b transit. This is the first bona fide rocky planet we ever found. This came out in 2010, just 5 years ago. And the lower here we see a pretty press image. So these are the image we tended to put out rather than the top left.
Boom boom bobby, boom boom bobby, boom ba baby. pressure pushing down on me, pushing down on you. No man has for under pressure that burns a building down, splits a family in two, puts people on streets. Boom ba ba ba, boom ba ba ba, dee-dee-do, dee-dee-do. That's okay. It's the terror of knowing what this world is about. Watching some good friends screaming, let me out. Pray tomorrow takes me higher. Pressure on people, people on streets. Da-da-da. Ah, ra-ba-ba-da-ba. Okay.